All right, we're back. Going to wait for people to show up. As soon as somebody gets here, maybe give me a thumbs up um, on everything being readable and audio being fine. All right, let's get started. Um, Yesterday we got most of key generation done, all the way to the actual matrix multiplications here. I think we'll probably end up taking this, moving this here, like it's done in ML-Chem, and saving S1 as entity in the entity domain, but we'll probably find out about all that stuff when we start working on signing. Because indeed the format that NIST uses for private keys is both useless as an internal representation and a very poor exchange representation. All right, let's not just get straight back to that. So instead, what do we have left? We did everything up to here yesterday. So now we got do this compression stuff. So the compression of t, I think, is simply for every value in t, we take the most significant bits and we actually put those in the public key. While the least significant bits we leave out because they're not needed, because the algorithm will work even with a degree of approximation will always come out to the same result. This is the harder math part that I don't claim to actually understand. By the way, if anybody could confirm in chat that audio is working, everything is fine. And this is shaken iced coffee. Excellent, thank you. Oh, hi, Deidre. Um, okay, so we've implemented this part. They they should make us do t1 and t0 here as there's a function power 2 round which separates t into the high and the low bits. But really, the high bits are needed in the public key. So I'm thinking of just putting the rounding in the public key encode function and passing t as is. And just when we encode it, we drop the low bits as we do the encoding. That will make this encoding harder, but again, we are never going to use this silly encoding. We will have maybe a separate file that does it for testing purposes, but I really don't want to make the actual implementation, the production implementation, harder just to support it. So let's go look at power 2 round. What does it do? Okay, there's high order and low order bits and hints. The specification uses the auxiliary functions power to round, decompose high bits, low bits, make hint, use hint, and explicitly defines these functions where R is in ZQ, which means just a number modulo Q. R1 and R0 are in Z, which means they're just numbers. And H is a boolean or equivalent an element of Z2, so yeah, 0, 1. However, the specification also uses this function where R and Z is in coefficient-wise to polynomials in lectures. Okay, so it's just saying that these functions are applied to apply these functions apply just to field elements, but if we apply them to polynomial, we just go coefficient by coefficient. So yeah, all right. So the one we care about is power to round, and it's just, yeah, coefficient by coefficient. Sounds good. Okay, easy enough. Support key compression optimization, dropping the D low order bits of each coefficient of the polynomial vector t from the public key using the function power to round. However, in order to make this optimization work, additional information called a hint needs to be provided in the signature to allow the verifier to reconstruct enough information in the dropped public key bits to verify the signature. Okay, makes sense. So we drop information from the public key, and then we have to put a small hint, which I think is just zeros and ones, or maybe -1, 0, 1. In the signature, which has a very compact format. Hints are created during signature and used in verification. In the verification of the signature, the hint allows the verifier to recover W1, which is the rounded W. Yep, sounds good. The signer directly obtains the W1 using the function high bits. And the part rounded off, R0, is obtained by low bits. Okay, so those are just functions that take the high and the low bits. Power to round decomposes an input into integers that represent the high and low order bits. Okay, yeah, in the straightforward bitwise way. Okay, so it's literally just the high and the low bits. Well, no, R0 is the mod plus minus, which is like the one with positives and negatives, but we don't actually care about the R0 part because that part is the part we need to save in the partially expanded key to reconstruct it, but instead we just save the seed and recompute it every time. So great. It might just be the really easy part here. Decompose, which is similar to power to round, except oh, I see. Decompose is different instead. It doesn't use just the bits. Oh, okay. Okay. So high bits, low bits make hint, use decompose, which split it not along a bit threshold, but instead along a divisor of q minus 1. But we don't care because we're just looking at power to round for now. And power to round is just okay, it's not literally just taking the high bits, right? So this is doing R mod Q. But R is always mod Q? I am so confused. R is an element of ZQ, which is the numbers modulo Q. So R plus is just R. Then R0 is R plus modulo 2 to the D, but modulo plus minus, which is just the annoying signed version of the modulus, because this spec really likes its signed integers for some reason. Mod plus minus. The unique element in the range minus q divided by 2 to q divided by 2, such that they're congruent modulo. Yeah. And then it returns R0 and R minus R0 then divided by 2 to the D. I'm not getting it. Also, I love how it says, oh, it in the straightforward bitwise way. I say we just try the actual straightforward bitwise way and see if that works, and this is just the most annoying way possible to describe it. Maybe they just really wanted this to be positive and negative. Okay. Cool. So if power to round is just literally take the top D bits, and D is probably a parameter. Where is D? D, number of dropped bits from T, 13. Then we can, D is the dropped bits, so it's the top 10 bits, I think. Because it's 23, yeah. Okay, so we can go and read PK encode. Duplicate tab, obviously jammed. And we can implement PK encode. PK encode. PK encode is just row, and then it takes T1, which is already clamped to bit len q minus 1 minus d. Yeah, okay. The public key, and it does this simple bit pack, which I'm sure is going to be extremely simple, for every element in T1. And this is, I think, this bit len here is 23. 23 minus d is 10. 2 to the 10 minus 1 means just 10 bits. They could have passed 10, but no. It's literally a constant, people. Duplicate tab, simple bit pack. So let's actually start writing it down. So func pkey encode. It takes, we said, a row, byte, and it takes t, and let's make it take the parameters, even if I'm not sure it would be needed. Then, For now, we will ignore all of the optimizations and just start with pk. Our pk is a byte slice. And we start by appending row. And then for I'll see, we did need the it's a vector of k, yes. What do we call each thing? Is there a letter from the spec? Z, apparently. No, W. Well, it's technically WI, but whatever. Okay, so for each of them, we need to do it's just integer to bits. Okay. So since let's unroll it. We want to apply simple bit pack to each to each element of a T1 as returned by power 2 round, which is here, which discards the bottom 13, the equal 13 bits. Okay, so it's 10 bits per coefficient. So the minimum common denominator, the minimum common multiple of 10 and 8 is 5 times 8. So 40. We have to do 4 at a time. Because 4 is going to be 40 bits, which is 5 bytes. Okay. So, yeah. And 4 at a time is fine because it divides 256. But we have to do it like this. And how is simple bitpack doing it? Wait. Now, each of W's is a ring element, so now we're talking. into there. Let's see if it can do it. So it takes I think this is right, but I think I will find it more readable if we do first how do we call it? Integer to bits, which does not hover. Okay. Let's call it C0. Oh, right, we have to take it from Montgomery. Right, yes. To encode it, yeah. Because it's the top whatever bits of the non-Montgomery representation. Okay, and then we append the first byte cannot be just C0. Is it little endian or big endian? Little endian, right? Little endian, okay. So little endian means, oh god, but it goes first to last, right? 0, yeah, because it just calls append with integer to bits. Okay. The first byte, oh, the first byte is 8 bits, so yeah, this is correct. So this is just the bottom ones. Then this one is shifted right by 8, right? Or with this, which is shifted left by 2, which is 8, 10 minus 8, yes. And why end? That end doesn't sound necessary. Yeah, it's not needed. This is 2 bits, and then that leaves space for 6 bits, which is, I think, what 0xFC was trying to be. Yeah, those are 6 bits. The ends are just not necessary. And I think also the parents are not necessary. Let's see if that's right. Well, that's kind of hard to see, so let's leave them in. I was hoping that they would get spaces around them. Okay, and it ends with C3 shifted right by 2. So this goes 2, 4, 6. And this goes 8, 6, 4. That looks right to me. And I'm going to do something silly to make it easier to read. Well, that didn't help. Let's just split them into bytes like this. Okay, this is acceptably readable. I wonder what happens if I take the parents out. Let's not do that. This is readable enough. Okay, I think this is the encoding. Good question from chat. How are we going to test this? In general, how is crypto code tested? I gave a whole talk about testing cryptography um, at GopherCon 2024, I think. So you can watch that. But also we have a lot of test vectors for edge cases in the Whiteproof project, which we started recently maintaining as a place to collect test vectors from multiple people, and multiple people already contributed just to these ML-DSA vectors. So we're going to run these. And I also want to do some mutation testing. I'll do some very rudimentary mutation testing on things that I know are dangerous. So I will just remove parts and check that we have vectors that check that those are broken. As in how are we going to test it right now while developing, we're going to take one vector out of those and check if it works with that. This is just FIP stuff. So let's see. I think we're almost done because that's the public key. And then there's this TR, which is just the hash of the public key, where H is, I think, still shake 256. Yep. So we're going to take a 64-byte hash using shake 256 and call it TR and save it, and then we're done. Okay, so let's check that we populated everything. Did we populate K? Yes. T? Yes. S1 and S2? Yes. KL? Wait, KL doesn't make sense. We should have P parameters. Oh, and those we did not. And did we not save the seed? We did not save the seed. Okay. Well, thanks Copilot for adding it for us. Okay. Trying to think what format we want for the public key. It will probably be another internal format that has a method to produce the encoding. So yeah, probably. We'll probably decide that when doing verification. So for now, let's have a func rev temp which does, okay, so faux here, which faux is that? Let's not put private stuff in there. It's faux. I keep calling it faux. It's raw. Geez. It's this raw, which is the first raw, not the raw used for the secret stuff. We could have called the very public and the very secret things differently, but no, let's not. Are we saving it? We're not saving it. All right, let's add just a temp pk byte slice here. And raw tnp and return. Looks good. And I'll use T. That's fine. Let's do it like this. Okay, we might have finished key generation. Now we can write a little test and see what happens. Yeah, okay. So and we go here and we grab a seed for the baseline, but this doesn't have the public keys, but thankfully I spent some time adding the public keys to these this morning. It's still in a PR, so we're going to pull it out of the PR. Sure. Lol. And let's also do the larger ones. Oh, the seed is the same. Okay. And last one. $87. It's not public key bytes, it's temp public key. One thing that makes Copilot a lot less useful in Go is that it takes as immodifiable the import line. So it will do things in stupid ways. Right. Ooh, let's try the trick. Let's see if it works. Nice. Absolutely unnecessary. Probably slower than doing the copy paste, but I'm just a big fan of this new thing. All right. Oh, hey, Zebra. Drum roll. Oh. Nope. All right. Can't always work on the first shot, huh? Is it fatal or is it... Alright, these should be error F. So we learn if they're all broken. They are all broken. Okay. First question, is the first part the same? Yes. Okay. So we got that far. They're very similar though. Like the last byte here is the same, which could be a coincidence, but they're very similar. Oh, I'm gonna hate that. How are they similar but not the same? Jeez. Working with linear algebra, this is fun. Oh boy. Alright, let's try to figure out where the differences are. Let's take the last 5 bytes, which we know are supposed to be the last 10. The last 4 coefficients. They're also not very similar though. They have bits that are the same. Okay, so um, it is approximate anyway, so let's convert each of these to bin. Is this the right order? No, this is gonna be big endian, right? Gee, I'm not sure. Let's stare at it for a little longer. The bottom byte is always right. The second one is right here, but then there's a small error here. There's a small error also here. And 08 is fine. There's a small error here. And then that's fine. This is fine, this is fine. A small error here. It's always the top nibble. Not here, actually. This one is just all over the place. I hate this. I swear to God, if would they described as the obvious bitwise way is not the obvious bitwise way, I will just I the straightforward bitwise way. Question from chat: is this implementation for work or just for fun? Oh, this is for work. This is gonna go into the Go FIS 140 module. Eventually make its which is in the Go standard library, and eventually be the backing of whatever we expose in the standard library. But we want to get started with certification with FIPS early because it takes like a year or two. So I want it in the next version of the module. Okay, let's think about the math of this silly mod plus minus thing. It's the value that is congruent modulo modulo 2 to the d. Oh god, they might have actually forced us to do a bunch of work here. To recenter that distribution. I'm gonna give up and look at boring SSL before I spend a bunch of time building something that's not needed. So it's going to be in ML-DSA.cc. What's it called? Power to round. Yup. Multiple constant time selects because for some reason they do the straightforward bitwise way, not in the sense of just dropping bits. Okay. So it starts by just dropping the bits, and up to here is fine. But then it does more stuff. Oh, it's because they want to round based on the whether the dropped bits are above or below half. It's like saying in decimal. If I said drop the lowest the lowest 3 digits from this number, you would probably, if I described it as the straightforward way, you would probably do it like this. But they actually want this because it's rounding, I think. Yep, that's probably what it is. Okay, so what does boring SSL do here? They actually drop the bits. Then they do a modular subtraction. Okay. Okay, so R0 adjust is just R0 minus 1. while R1 adjusted is just R1 plus 1. So essentially it's saying it's preparing to, okay, and then it's doing a constant time select between the adjusted, which is -1, and R1 plus 1, based on if R0 is more than 2 to the dropped bits -1. Okay, so if it's more than half, okay. We can also do a constant time select. I think there's a slightly simpler way to do this for us. So we're not actually caring about getting the lower bits. We will care about that for the silly NIST encoding, but we can put that, yeah, to be fair, power to round does sound like that. I just would not have described it like they have, but yeah, fair. Okay, so essentially we have to subtract, no, add 1, right? Because it's like here, we added 1 from 27 to 28. If and only if the top dropped bit is 1. Right? And here, Boring SSL is doing it in a fancy way by doing a less than. But really, is this right? This is a less than, not a less than equal. And it's asking if, oh no, yeah. 1 shifted left by dropped bits -1 is less than R0. So R0 is higher than 2 to the, oh no, higher than 2 to the drop bits, which is 13, so 2 to the 12, and that's it, not to the 12 -1. So we can't just look at the top bit, because if it is 2 to the 12, so it's top bit set, everything else not set, then we still have to, okay. Fine. Okay, we do this with subtle. Where do we do this? I guess in a new function. And might as well return them both at this point. R0 is the low one, right? R1, R0. How does it do it? Oh, that might actually be right. Because if we add a certain value, it will wrap. Although we will have to do a reduce once, I think. Right, so let's start with um, that. Dorps. Okay. So if we try to do the addition method, if we try to do the addition method, then I just hate this representation. Let's look at this one. We need to flip a bit if R0 is higher than 2 to the 12. I already forgot. 2 to the 12. So 2 to the 12 plus 2 to the 12 is 2 to the 13, so it will go all the way up. But if it's any less, it will not overflow. So if we just add 2 to the 12, this will work. The problem is that what happens if the value was already about to overflow? Here it just does +1. How does it handle? How does this handle overflows? Oh, R is at most Q. R is at most Q, right? And Q is 2 to the 23 minus 2 to the 13. So if we add 2 to the 2 to the 12, it will still not overflow 2 to the 23, so it can't overflow. Okay. I think I'm reasonably satisfied. Now it stops suggesting the useful thing. Let's see what it was suggesting. Now it's not doing the useful thing anymore. Okay, but we can do it for it. So I'm not convinced that this is correct. So R mod Q. Oh no, yeah, they just do the subtraction here. but it could be negative, so it could go higher, and then divide. So it is fine for it to overflow. Okay. All right, this should work. Let's try it. Nope. Although this is only one of them. What? Which one? Oh boy. It all they all work except the 87 one. Okay. Let's figure out how different they are. Progress. I know this is the slowest possible way to compare these, but okay, this is the part that's different. We're essentially binary searching them. Somewhere in this line. Here it is. I think it's this one character. Yup. It's wrong by one character. One bit. No, the FIPS does not provide the test data with the standards, but there's test data provided by the ACVP demo vectors, which one can use. Although they just give you random test vectors, while it's much more useful to have specialized test vectors like the ones in Weichproof that try to hit complex things. Although sometimes random test vectors also work for things like this. For example, this has a space of 2 to the 12 or 2 to the 13 in which things can go wrong, right? Which means that if you run a few thousand tests, you are almost guaranteed, like let's say 100,000 tests, you're almost guaranteed to hit every edge case in spaces that are that small, which is probably what's happening here. So we must be hitting a very edge condition on the low bits of this one. It's 1 bit at the bottom of this byte, because the difference between 2 and 3. Is this even or odd? Odd. Odd. How many? 2615. So these are 2615 characters, which means 4 bits each. That's 10,460 bits. So that's divided, can be divided by 10. So it's the bottom bit of a byte, and it's higher than it should be. Haha. This is higher than 2 to the 12. But right now, if it's equal, we are overflowing. So the fix is -1. Yeah, see, we even had it written wrong. Woohoo! Nice. All right, we've got a functional key generation. We could even get started on signing. Let's do that. There's a few things to clean up, like, of course, the temp PK part, but that will get cleaned up with verification, not with signing. I'm not doing this part, definitely not now. All right, so signing. Signing has the whole hedging, not hedging thing. But I think that's in the external function. Let's see if there's anything interesting in there. It checks that the context is not too long. It takes randomness or zeros. And then it encodes the message representative, which instead I think we're going to delegate to the internal sign for now. Yeah. Yeah. Right. Trying to think if we want a top level sign function that takes a private key or a method on the private key. The reason not to have methods usually is to allow the linker to drop unused code, but at the same time, we'll need a method anyway to implement the signer interface. However, that method will probably will have to take options in the way that is expected of the signer interface. So instead, we're probably better off with a func sign, which is a top level fine. But let's start with sign internal anyway. Sign internal will take priv. We'll take message. Context and random. Lol, implementation of omitted for brevity, sure. And random needs to be 32. This one doesn't need. This one can never be hit by users because we're just going to generate it for them in the sign caller, but sign internal is gonna be needed for testing. We'll probably have a testing only version that takes that, and then sign and sign deterministic. Yeah, something like that. Actually, yeah, let's write those already. There. Bye. Thank you for stopping by. Okay. Now, we've got to start by encoding the actual message, although we're probably going to hash that. So let's just keep this open and while we implement sign internal. It starts by entitying a bunch of stuff and expanding a bunch of stuff, which instead we'll just have in memory. But where does it operate on the actual here? Okay, so what is TR? TR is the hash of the public key, right? Which we forgot to do in key generation. Yeah, it's the shake256. I even went and looked and vocalized it and then did implement it. Good going. We said 32 or 64? 64. I wonder why 64, but okay. Okay. So we've got TR. Now, let's do the message encoding, which is mu. We start with H, which is a shake, and then we write bytes to bits of TR, which is just a way to say write TR. Then we write M1, which is the thing that was done here, which is at 0 byte to distinguish from pre-hash. Then the length of context as 1 byte. That's right. Context and message. And then we read mu from it. Good code, except I like better to do. Good bot. And it's 64 byte. Sounds good. All of these entities will probably try to. When you say that error is never hit by users, why did you make the content check error private then? A user wouldn't be able to check against that. Yeah, so I mean, generally, I actually just use errors.new, but somebody had suggested hoisting the error just so it can be compared. I'm not entirely sold on that, honestly, but at least I guess it will return an error that is always the same if context is too long. So you could, in testing, do an equal. I'm not super convinced. We could also expose those errors in the future, but I feel like I don't know. I'm generally allergic to having a lot of API surface because there are things we are going to be bound to forever, and if for some reason it becomes hard to distinguish errors, we are bound to doing that. But I don't have a good argument for why making it a variable but not making it exposed. I think you're probably right that it's neither here nor there. When we think through the actual API, we'll think about all of the exact things to expose, and there's going to be a proposal, and we're going to discuss that. Right now, I'm just focusing on the implementation to get it into the FIPS module. This is not the exposed API. Okay. Private random seed, another row, this time with 2 apostrophe. Okay. Where do we use it? We use it to do expand mask with the counter for the rejection because because this is a Fiat Shamir with aborts, which is essentially a rejection sampling for a whole signature. We try signing, and if this signature comes out valid, like not valid, I think it's if it comes out in such a way that it doesn't leak values about the private key, we keep it. If it has too high coefficients, we try again. But before we get there, all of this stuff we need it in the entity. Wait, why do we need the T0 in the entity? Uh. So apparently we do use the T0s in signing. Thanks, I hate that. But we use them by always multiplying them by the C, which is the entity of the sampling of the challenge. So it's just the hash of essentially the hash of the message plus the challenge value. I see. So we needed to multiply by C, which is a ring element. Okay, now we do need to save that too. Although we can save it already in the entity domain. Okay, so let's start by moving S1 and S2 into the entity. And then apparently we don't need T at all. We only need T0 saved. So I guess we're gonna save that. Okay, so step 1. These are entity elements. And we remove the to-do. This will have broken some stuff. And we can take them into the entity domain. And then we don't need two entity fins while we do that. And that was simple enough. Why does the NIST private key encoding have the known entity and then every time you start signing you do the entity for those? Who the hell knows? T instead. T sounds like we can just make it up for now. Oh, but here it needs to be outside of the entity? Wait. This is silly. Why do we take the result of the multiplication out of the entity every time instead of doing all of the additions and then taking it out of the entity? I guess the faster thing here is to no, let's keep it in the entity. If I understand the entity correctly, we can do addition operations inside it. So instead of doing all of these inverse entities, we do one final inverse entity at the end. I wonder if this still works. It does. Okay. And I think it's actually testing it because T is then the thing that we're encoding. Okay. Sure. Um, I think this is faster because instead of taking something out of the entity S1 is L times K times, it does it only K times. Seems better. Okay. Now we have to persist the lower part of power 2 rounds. So we do have to implement the part where okay, so we need to understand why it subtracts 1 when rounding the one above up. So I understand why if it's above that, you round up R0, R1. Why is R0 subtracted modulo 2 to the 13? So if it's 0, it becomes 0x FFF. So if we round the other one up, oh no, I'm misreading mod sub. That's why mod sub is this minus that in modulo q, right? Oh come on. There. Yes. Okay, that's a minus b modulo q. Okay. That makes more sense. So if we are adding 1 to the higher thing, we have to subtract modulo q 1 to the yeah, okay. If we add it to the high, we have to subtract it from the low. And now the question is how we do that, because I felt very clever doing this, but this does not make it easy to do the, oh god damn it. Cool. We have to actually implement it like boring SSL does. I don't see another way. This is a cutesy way to do it for and it's also very annoying because then we actually have to split it because we can't keep it inside PK encode because we have to move it all the way out so that we have a T0 to multiply by. Oh jeez, I hate this. Because then we do C times T0 and then we make the hint based on yeah, I bet there's a way to make this cleaner by reaching in to make hint, but I think it would make it a lot harder to review. So no, let's actually do the work of splitting that into a T1 and a T0. I'm really... Well, I guess we don't care about performance in keygen, right? So we could have two separate, because I don't even know what type to give T1 and T0, which is why I liked passing the actual T in here. I wonder what high bits does. Oh no, it uses decompose, not power to round. Did we have to have two different ways to do the same thing? It's just more code, more opportunity for bugs. Okay. Okay, and when we multiply, when we use it, we're gonna need it in the entity domain, so we might as well also entity this one, right? So T0 is used here, where we do need it in the entity because that's the first step we do there. So we might as well pre-entity it. Okay, I think this one... Um, and we return a field element, so it's already in Montgomery. But we have to start... What does it suggest? No, that's not it. Okay, this one we have to do like boring. R0 is either R0, which is just R minus R1. But wait, if we have R1, we necessarily also have the R0 value, right? Because R1 times... Yeah, we can take R1, shift it left, and do a subtraction. A modular subtraction. Yeah, that will work. Except... shoot. Except R1 shifted left by 12 bits might be more than Q. so it overflows the bounds. Yeah, like what I wanted to write was so we take the value, we subtract the correction, but that's not. Because the only thing we have that we can use is field reduce once, which however is a conditional subtraction by q. And yet it feels like the bounds should correct themselves. Let's try it. Let's try it. So R1, right, so this is it. Thank you for stopping by and for the comments. Okay, so R0 is going to be RR minus R1 shifted left by 13, except we want that to be a conditional, so what I wanted to do here was add q and then do a reduce once. But that's not gonna work because R1 shifted left by 13 might be higher than q. So this might still end up negative. Although I think that's not actually possible. Because for R1 to be higher than q, it would have had to round up all right, let's write out the bounds. Okay, so when we shift it to the right, so it will work out to 2 to the 23 minus 2 to the 12. But that's not enough. Wait, is that the right? If I have a value that's less than 2 to the 10, right? Okay, that's more like it. Yeah, because when we look at it with minus equal, if you have something that's 0xFFFF and you shift it left, you don't get a longer string of FFF, you get zeros at the bottom. Yeah, so, yeah. So RR is Q. Need to remember what Q is. Two to the 23 minus 2 to the 13. Oh, but that's Q minus 1. I'm just convincing myself that I can call reduce once. Or rather, directly call south to Montgomery, which we need to make into wider. Yeah, there's going to be a sub to Montgomery. Wait, oh, this is much easier to separate as a reasoning. If they're both less than q, then if we subtract something that's less than q and then add back q, we can do Phil Montgomery. Oh, also this is a mole, so actually we're way safer. We could go way higher, but even just with less than q would be enough. So let's go to where this is used. It's used with values that are bytes, but we just need to make it on uint 32s. And then we just use this. Um, what type is R1? Okay, so we know that R1 times that is less than or equal to this value, which is less than Q, so we can pass it in here, and that's our R0. Okay, this was easier than spent a lot of time thinking about it, which I appreciate everybody just sticking with me while I did that. But yeah, that's it. Okay, with this we broke the types down here. fixed the types here. And I like that we're not mixing Montgomery and non-Montgomery. Oops, oh, that's a good catch. This was gonna be an annoying bug. Hey. Okay, so now that we have power to round low, we can go back all the way up, add the T0 list of T0 is an array of entity elements because we're going to entity each of them. I think we have to invert the entity before we can go element by element. This will not work because we wrote it right, we wrote it component wise. Instead, this is a list of entity elements. So this might be it. But then we have 20 T. So actually, first let's do T0. Well, more like W. Okay, we could also loop 2 times. It's probably gonna be more readable, isn't it? Okay, so this way we have T0 already saved in the entity. Although the pattern we've used is that every time we loop, we're hoisting it out beforehand. So let's do that. We have to change the name of this. What do we call this? just W. Just W is fine. Okay, and let's nope. Let's see if this works. I kind of just wanted a way to explain what we're doing here compared to the spec up here. Because the spec up here has us do T directly. Instead, what we do is a hat times S1 hat. But I kind of want the ability to how to type. Haha. Option I plus letter. Cool. So this is, the first part is option I, T. Oh, that didn't work. Oh, because apparently you can't circumflex a T. Okay. But you can IA. Sure. Okay. Hat T is hat A times hat S1 plus S2, yes. And those are both hatted, yes. Then we do T equal inverse entity. Is that how it's written? No, it's entity minus 1. Well, this is instead hat T0. How do they write it down? Power. Okay. Very annoyed that there's not a hat T. But okay, I think this will give us the priv T0 we needed. So with that, we've pre-computed actually all of these steps. So since we're doing that, doesn't actually look any better. We've done this. Expand A we've pre-computed. So we have to do this raw, which is used for the mask. So we're gonna call it raw mask. And we write K, which by the way should not be an uppercase, or it will be exported. Whoops. Same with A. I made the same mistake in ML-Chem. I had initially exported the matrix A because it's written uppercase in the spec. Random, and then the method representative. Yeah. They calls it the random seed. Is it the nonce effectively? It is essentially the nonce. Yeah, it is. We're gonna call it a nonce. That sounds good to me. And it's 64 bytes. Correct. Okay, and then we do the loop, which is the actual signature. So if you're curious about the math, it's actually explained pretty well around here. But it's essentially like a ED25519 signature. So you pick hash of both a value that you randomly generated and the message, and then you do the hard computation to it, and then to show that you actually knew the private key, you show both the random value and the hash. Probably the worst explanation of Schnorr signatures you ever heard. Anyway, 4. Fine, we'll use that. Plus equal L? What is that used for? Where is the exit condition of this? Oh, the exit condition is when those are not valid. So essentially, if you reach here, you exit. So you could just return, you know? Oh, jeez. I'm not finding... Oh, it's used here in expand mask. Okay, time to go look at what expand mask does. Expand mask takes our random value and a counter. It samples a vector such that each polynomial has coefficients between minus that plus 1 and plus that. it takes a seed row and a non-negative integer. Yeah. And it does. C is the bit len of that minus 1. Row is concatenated with a counter, which starts at, okay, that's why it adds L to that counter as 2 bytes. Okay, then we do a H of that plus that. Okay, so far so good. It reads 32C and then it does a bit unpack. Oop. Let me switch that back. Okay, so we need to implement bit unpack. Oh, you know it's not going well when there's simple bit unpack and bit unpack. Used to decode byte strings produced by the above functions. For some choice of an A and B, there exist malformed byte strings that will cause 12 polynomials whose coefficients are not in the ranges, respectively. This can be a concern when running on inputs that may come from an untrusted source. Ah, okay. Like, thank you. Sometimes it will just not work. Deal with it? Is that what? For some choices of A and B. When A plus B plus 1 is a power of 2, the coefficients are in minus A to B. Okay. What values are we calling it with? A and B are that minus 1 and that. Now we need the 2 to the 17, 2 to the 19, 2 to the 19. So it's a power of 2 minus 1 and a power of 2. And this is saying that it's fine if they are added are a power of 2, which they are. Okay. So it does bytes to bits, then it extracts a polynomial, okay, with coefficients in that range. Where C is the bit len of A plus B. And here A plus B is the thing minus 1 and the thing. Which is a power of 2. So it's 2 to the 17 plus 2 to the 17 minus 1, which is 2 to the 18 minus 1, and 2 to the 18 minus 1 has 18 bits. So I think C is 18. All right, let's start putting these values in, which are 17, 19, 19. We're going to put them in the parameters here. And we're going to put the logarithms. No, what? I was about to say, oh, it knew them, and I nope. Okay. Uh, bit unpack with C equal 18 and C equal 19. I think Boring SSL just wrote separate bit unpacks for each of them, so I guess we're gonna do the same. What it does is that it goes through each, and for each of them, it sets it to B minus bits to integer. I see C plus 1 all the way to C plus C minus 1. Okay, IC is just skip the first whatever bits. And it's just bits to integer of the next C bits, right? Yeah. And we need to go look at what bits to integer is. Little endian bits, okay. I mean, oh god, 18. Okay. By the way, this stuff is probably in the wrong place here. We should move it to the field file. And still in this file, we'll probably write our 15 different bits to integer. Not bits to integer, sorry. Bit unpack. What's the difference between bit unpack and simple bit unpack? Oh, simple bit unpack does not do the negative ones. Okay. And it returns a polynomial. It was right. So negative a. Negative a is minus plus 1. Okay. So much betwiddling. Oh. How does one even do that? What's the minimum common denominator of 18 and a minimum common multiple of 18 and 8? Oh god, it's 72? So we need to do 9 at a time, I think? Because 9... No, we need to do 8. Or we need to do 4, wait. Oh, because 72 divided then by 18, which is 4. So we need to do 4 at a time. So that 4 will be 72 bits, okay. And then for each of them, we need to extract the value in little endian. And then we need to do this conditional subtraction modulo. No, wait, this is not modulo. This is just a subtraction because we know the value is less than. No. No, right, because it will be negative. So we need to do a conditional subtraction. Although we know it's... it's another field reduce, blah, blah, blah. Very happy with that. Where did field go? Oh, this is field. Very happy with this field sub to Montgomery because it's really the interface we keep needing, doing a subtraction and then bringing the result into the Montgomery domain. Saves a lot and keeps the interface safe. Okay. So who knows? That might be right. Oh, So it's taking... We can make this more readable by doing v equal... how many bytes is it? It's 4 times 18 divided by 8. So it's going to be v0, v1 shifted by 8, and v2 shifted by 16, but that's not enough. Because we need to take only the top 6. No. 8, 16, we need 18, we need just 2 bits from this one. Okay, so we shift that one right by, that one left by 6, that one left by 14, and then we've used. So then we have 8 from here, 6 from here, so that's 14, and we need 4 more. This is the part it really can't count, huh? Wait, where is the parent? Oh, I guess that's smarter. All right, that's cleaner. All right, 2, 4, 6, and then the last one 0, which sounds right. 2, 4, 6, 10, 12, 14, 16. Okay. And we need to do bit unpack 20. Geez, I really hope I got the right numbers, otherwise I'm doing all this for nothing. How many do we do at a time? 20 divided by 2 divided by 2. I think it's just 2 at a time is enough. and then we just used 4 of those. Shifted left by 12. Yep. Although 5? No, 2. Okay. We've got our bit unpacks. Let's just make a top level func bit unpack. Yeah. There we go. And back to where we were. So this was pretty deep. We were there because we were doing expand mask, which was doing, which was computing y. And for each of those values, it was expand mask was passed a row and a counter. Okay, so y is set. Trying to decide if we should entity it now or not. Looks like we need it for z, which needs to not be entityed. So we don't entity it. Okay. So we have got y, which is is it KL or LK? KL. It's a ring element. It's a vector of L ring elements. And they're generated by expand mask. Expand mask does it by doing might as well call this one R like they do. And then we need to do 32C. What is C? C is the 1 plus the bit len of why talk in terms of bit len of that minus 1 instead of talking about, anyway, just log 2. But okay, so this is 18. That's the thing plus 1. Oh, that's just the length of the input for, yeah, sure, okay. So v is make byte 32 times, let's use our calculation for that, which is times n divided by 8, and we do that on, we said priv.p.log plus 1. Let's call this one C. Okay, so we instantiate a h. We could just reuse the h. I think it's less than the rate anyway. So yeah, let's just h.reset. And we write nonce. And then we write the addition of those two values as a uint16. Okay. We can do that with little endian, like everything. Let's put things a little more in order. Okay, so I think that's our v. And v is passed into I guess we could avoid returning the error here. It's not like it's gonna get called by anything that will ever actually fuck that up. So yeah, I think that's fine. There's just no chance that this is called by anything that's not a thing where we just calculated it, so. I never did the little endian put. Oops. Looks like someone was lazy. That someone is me. This is just a trampoline package that's there to capture calls to what? Oh, interesting. All right, let's just put in the one I need. This is a package that's the only reason it exists is so that we can keep stable internal dependencies for FIPS modules that might need to get used for a long time in the future. So we don't want to use internal packages like internal byte order because those might not be stable and they would have to become stable to be used by a module that might keep getting used in the future. So instead there's just those wrappers, and at least it's the problem of the crypto people, not of the okay. I think this is the sampling of y. And then there's this pretty multiplication. Should be easy enough. Let's go copy paste it from here where we know it works. So it's going to be, and it's called W. W entity -1 of entity y with no addition. Wait. It's not the same operation. That one had a transformation by a vector, this one does not. So it starts at 0, I think. Is that 0 entity element at 0? I'm not sure. What's the entity of a bunch of zeros? It's a bunch of additions, of multiplications by things that come from the thing itself. So I think that 0 is the 0. So I think we can just drop it out. We should do the additions in the entity before we come out of it. So yep. Yep. Okay, which reminds me something in ML-Chem. Wait, this is silly. We are inversing the NTT before doing the additions. We could do it after. Did we just find a nice little speed up in ML-Chem without realizing? Well, we need to put into the NTT E1 because it's sampled outside of the NTT. Such inconsistent specs. They sample the matrix A in the NTT because they say that's more useful, and it is. And then so yeah, we could make this entity element. Entity this right after sampling, which no understand. Maybe it's a special distribution. Okay, fair enough. And then we do var u hat entity element. Actually, we do u hat that. Okay, if let's see if it still works. Is this the only place where we do that? Yeah. They still pass. So this gotta be faster. This should have fixed the 1024 too. Yup. Let's test that it still tests pass. And then let's do a bench diff. Maybe it will not matter because those are kind of short vectors, but actually, how short are they? Well, it's 256, right? No, wait. No, it's this. It's just 4. Okay, we did not, almost certainly did not save a significant amount of time. It's either 4 or 3. So we're doing 1 instead of doing 4, but also we're having to do the entities for these, which are case. Wait, I think we didn't gain anything. Sad. Because we're having to entity these. And entity takes about as long as inverse entity. They're very similar. So now we're doing k-entity operations and 1 inverse, while before we were doing k inverse. This is worse. Lol. This is worse. So it will probably show in the benchmarks as being worse. Let's try it. Let's see. Surely benchmarking while live streaming is silly, but this bench diff script is a thing I wrote to make my life immeasurably better when doing benchmarks. All it does is show run the benchmarks at head, run the benchmarks with the working directory, or you can choose the base. It does it in a git git work tree, so it doesn't touch your files. It's built to also work with the standard library, which needs a couple tricks. As you can see without reveal. What? 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 Okay, what? Ah, okay, no. Okay, so before we were doing, it's a double loop. So before we were doing U is K, R is K, so K squared inverse entity. After we're doing and K is after we're doing 3 inverse entity and okay. And K entities. No, okay, this does save some time. It's just that much time? Okay. Fair enough. Yes, if you joined on me just going what, it's a good what. I realized while implementing ML-DSA that we were probably doing ML-Chem a little inefficiently. Then I had briefly convinced myself that actually didn't matter because I did math wrong. And instead, it does matter a little because we're going from 9 entity operations to 6. it's making things a lot faster, which I did not expect. But okay, hey, we just made MLChem 10% faster. Sweet. I guess. Yeah, because I was doing each multiplication and then taking it out of the NTT before doing the additions. So yeah, in lol. So here we're doing one of these, and I was doing inverse NTT on each multiplication result instead of doing it on each addition result. Yup. I think we can even save one more. Because we don't have to NTT this one. We started at a 0. And then we do the addition. So this went from 9 inverse NTT to just... Yep. I wonder if there are other places where I'm being silly like that. Let's run another bench diff. These seem almost too good to be true. I don't want to touch anything because it will interfere. Yeah, what? We're spending all that time doing inverse NTTs unnecessarily. I'm gonna quickly audit all the places where I'm doing inverse NTT. Be right back. Oh, this is so silly. This one is post multiplication, that's right. This one is post multiplication. This one was the silly one. And now let's find all of the NTT calls. This is almost embarrassing. So we're NTTing things here, which are going to get used in both those multiplications, so they have to be NTT'd. We're NTTing things here. Which is doing it to the ciphertext. Why is the ciphertext not written down in NTT already? It would be faster. Anyway, nothing we can do about that. Yeah, this one doesn't look like we can do anything about it. And then there's 2 over here. S, which we're going to use in multiplication, and E. This one we can save. Or maybe not. No, T is kept in... Where is T used? Oh, T is kept in the entity domain, specifically because then we need to use it for this multiplication. So it makes sense that we keep it, we entity it, and we keep it in entity. Yeah, all right. All of these have to be entitied. Yeah, all right. Let's ship this. Lol. I kind of want to redo the bench diff because that can't be right. The waiting for the benchmarks. Yeah, it's real. Jeez. Wow. Wow. This is a little embarrassing. um, Okay. Well, having taken this little aside, which we're going to mail by doing this. All right, we've shipped that one off. Oh, okay, one sec. Okay. Right, we've shipped that one off back to us in ML-DSA land. We had just figured that out because we just avoided doing the same silly thing here. Right. I can't even blame the spec. The spec is applying the entity to the matrix result, not to the addition. So no, they were doing it right to the matrix multiplication result. So, oops. Oh no, high bits. What is that for? What is W1 used for? Is used for W1 encode. I might not have the brain power to do this part. It's just the most finicky, annoying stuff, the rounding and so on. I think we might take a break for the day on having done W. Yeah, I think so. Yeah, alright, we computed Y, we computed W. Got far enough. We have key generation working, which I'm pretty happy about. It means that all of the Montgomery stuff is right too, and then TT stuff is right, so yeah. Cool, folks. If there's any questions, now is a good time to ask them. I think I'm going to save this as a work in progress. All the things we've done today. These ones I'm mailing in as work in progress just so that I get some tribot running and so that I don't lose them. But I'm going to then abandon the CLs and make one single CL for ML-DSA. Hi, Roland. um, okay, so will you have to review this before the freeze? Arguably not. We have to review this before we freeze the v2.0.0 module. But since it's just going to be an internal package with no exposed APIs, I don't think that freeze has to apply. Maybe? What do you think? It's also very similar to the ML-Chem. Oh, and by the way, you missed this, but in the process, I just found out I was being very silly with where I was doing the inverse NTT here. I was doing it inside the inner loop instead of doing it outside of the inner loop. So I might have. The good news is I've just made ML-Chem 10 or 18% faster, depending on which side you are. The bad news is, of course, it was unnecessarily slow. Yeah, you saw that show up in the review queue. It does mean that we have to wait after the freeze to freeze v2 FIPS. Yes, but also I feel like we should wait a month or so before freezing the FIPS module anyway, because there's always some stuff that might come up right after the freeze, right? Bug fixes and so on. And it'd be very annoying to have to do another rewrapping of what v2.0.0 is. Not as annoying as the rewrapping of v1, which had actually shipped, but yeah, so what I was thinking is soon after the freeze, we open a CL that does the freezing of v2, but we don't land it, so we get some builder coverage to it. And then after a month or so after the freeze, then we do the actual module freeze and submit it. But yeah, we can think about it. Cool. All right, folks. Any questions? Otherwise, I'll take a break, get dinner, and then maybe if I still have energy, do a bit more in the evening. We got all the way to here. So quite a bit of stuff left, although most of it is pretty simple. It's just the encodings that are going to be annoying. And then we'll have signatures. All right. Also, it looks like people are showing up now, which fair. It's 11 in San Francisco, so good morning. It is 7 p.m. here now. So yeah, dinner. Probably back after dinner to finish signing. So Roland is asking if I ended up splitting the entity stuff out into its own package. No, because it's actually a different entity. While the ML-Chem entity is it maps to 128 extension fields. This one maps to quadratic extension fields, so essentially just 128 tuples of two field elements. This one maps to 256 field elements. So I think they're fundamentally different. We use them the same way. So if you haven't seen it yet, I've written an appendix to the explainer blog post with what is different about ML-DSA, and it's very little. There is that technical difference, but it just means that entity and inverse entity are different, but those are just implemented from the spec. Multiply entity, instead of being a large chunky thing is just component-wise multiplication, because it doesn't operate over those quadratic extension fields. The base prime is bigger, so we end up using Montgomery form instead of using just plain form with Barrett and Barrett reduction for the multiplications. And that's pretty much it. Oh, and instead of being all matrices k by k, they're k by l, and that's pretty much it. Oh, and then there's a lot of annoying stuff with signed distributions, positive and negative, which we obviously don't implement with signed numbers because that would be unreasonable. But that's mostly harder to read the spec, not really to implement. They're very similar, so the difference are super small, but I don't think we could actually reuse any code because the prime field is different and larger enough that in one place we use Montgomery, in the other we do not. And the NTT is similar in how we use it, but it's different in how it's implemented. So I think it's just useful to have read MLChem before implementing ML-DSA or reviewing it, but I don't think there's actually any code to reuse. There's still the concept of zetas, but the zetas are different. Yeah, I think it's just there's sampling, but the sample which I basically copy pasted, but the sampling is from different sizes and distributions, so it's not reusable as is. It's just very similar. This stuff is all new. This stuff is new. No, I don't think there's any actual code reuse. There's a lot of concept reuse. Yep. Cool. One thing we'll have to decide is for MLChem, I only implemented 768 and 1024, and I wanted to hardcode the 768 sizes for speed, I guess, even if I was leaving on the table a lot more because of that bug. Whoops. So I have that generator that makes the 1024 by modifying 768. For ML-DSA, I think we probably want all three. Yeah, if Boring is using C++ templates, that there might be more reuse. But even there, I think I've looked at ML-DSA.cc and it's self-contained, I think. So the question is, what do we do about the different parameters? Right now, the private key struct in memory just takes as much memory as it has to take for the largest private key, which is, well, damn, 81 kilobytes. It could be less for the smaller parameters, but what it does right now is it has space for all of them, so it will do a single allocation. And then it just uses sub-slices of those, and the code is shared. The API, I still exposed the sizes separately. We could also expose the parameters as an actual enum of a type that can be passed in. I'm not sure. Yeah, we need to think about the API. An interesting question is 81 kilobytes too big, and do we want to save on memory usage for private keys of the smaller parameters? Not really sure. Yeah, maybe exposing parameters is not such a bad idea. We give it a name field, and then we have the sizes, the signature size, private public key size, private key size on those, so that people that want a constant for that, well, but then they would not be constants because they would be in a struct. under parameters. So actually, no, maybe not a great idea. Yeah, well, yeah, 81 kilobytes keys exactly. We'll think about it. All right. If no one has any questions, anything coming up, I'll sign off and I'll see folks again in a few hours probably.